Hello there. We are continuing our adventure in volumes of rotation. Last time we were either rotating about the x-axis or the y-axis, but hey, why stop there? We can rotate around other axes as well. We don't always have to revolve a region about the x-axis or the y-axis to find volume. We can pick a line parallel to either axis. Depending on the problem, we can use the disk or washer method, just as we did before when rotating around the x or y axis. Let's say we want to rotate this blue area here around the line y equals c. That's up here, so we're rotating this blue area around the line up there. Now, we're going to have a big R and a little r, just like we did before. And the big R is going to be from the axis of rotation to the furthest part of the area. So in this case, my big R is going to be that distance right there, which is just c. And then the little r is going to be from the axis of rotation to the closest part of the area. That creates the whole. So that's c minus f of x. So you take the whole distance to c and then subtract the height of the function there. And we can plug that into the formula that we've been using all along. So we've got pi times big R squared minus little r squared times the height. And the same thing happens when our axis of rotation is below the x-axis. But it's a little bit trickier here because again, the big R is from the axis of rotation to the furthest part of the area. And that's going to be f of x minus c. Now, this minus c can be a little bit confusing because if the axis of rotation is below the x-axis, what you're doing is you're saying f of x minus, and then c is a negative number. So it ends up actually being f of x plus that distance here, which is c. That gets a little bit tricky. And then the little r is just 0 minus c. And again, if c is a negative number, you end up with a distance of positive c. So let's put that into our formula. We've got big R squared minus little r squared. Now, sometimes you might have a floating function. It doesn't go all the way to the x-axis, but that's fine because, we're still going to do basically the same thing. Big R is going to be from the axis of rotation to the farthest function, so c minus g of x, and little r is going to be the axis of rotation to the closest part of the function, so c minus f of x. And then, plug it into the function like we've been doing. Big R squared, little r squared. And the axis of rotation could also be below the x-axis. And again, that's where it gets a little bit tricky because we've got f of x minus c, but because that c is on the bottom side of the x-axis, what it essentially looks like is the height of the function plus this gap right there. Minus negative c is a plus c. So big R would be then f of x minus c, little r would be g of x minus c, and in it goes to our formula. All right, we'll actually try some here. The volume of the solid generated by rotating the following region about the line y equals 4. We got y equals the square root of x, y equals 0, and x equals 4. So if you don't have a graph given to you, it's really helpful to go ahead and sketch it. So we're going about the line y equals 4. It's up here. So we need a big R and a little r. The big R is going to go from the axis of rotation to the farthest part of the area, which in this case is the x-axis. And then the little r from the axis of rotation down to the closest part of the area, so 4 minus root x. And then you can plug those into the formula, pop it into your calculator, 108.908. And I don't think I have this on the rest of the slides, but would you please label those as units cubed? All right, we'll try another one. Find the volume of the solid generated by rotating the following region around the line y equals -1. This time, our axis of rotation is below the x-axis, so that's when it gets a little bit tricky. And then the line or the function y equals 4 minus x squared and y equals 0, the x-axis. So let's sketch it there. And then we need to find a big R and a little r. So the big R, it has to reach the height of the function and then continue on to the axis of rotation. So let's see, we've got like the function here, f of x minus c, but because c is a negative number, we're actually doing 4 plus 1 plus that little gap there. So 5 minus x squared is big R, and then little r is just going to be that gap there. 0 minus -1, which is just 1. And then that goes into our formula for a cylinder. Remember, the cylinder is big R squared, little r squared, and the height. And we'll integrate that from -2 to 2. Oh, where did I get -2 to 2 from? That is where the function 4 minus x squared meets the line y equals 0. So you'd have to solve to see where those two lines intersect. And then plug that into your calculator, and you get 174.253 units cubed. We can also use an axis that is vertical or parallel to the y-axis. So in this case, if we've got x equals c and we're rotating it around that, the same thing holds true in that big R is the distance from the axis of rotation all the way to the y-axis. That's the farthest part. And then little r is from the axis of rotation to the closest part, or the area. And again, that little r, you're taking the whole distance to the farthest part and then subtracting the height of the function, which goes from the x-axis to the function. And then we know big R, we know little r, and we can put those into our formula there. And then let's see, if x equals c is to the left of the y-axis, that means it's going to have a negative c. So we're going to do f of y. We're going to cover the distance here, and then we need to consider that distance here. So it's going to be f of y minus c, but if c is a negative number, then to some degree, you're adding that distance. And the same thing, little r is going to be 0 minus c, but because c is negative, going to end up adding it. So there we go, big R squared minus little r squared. So again, we may have some floating areas that we need to rotate, which is fine. The big R would be c minus g of y. And again, I'd like you to go, it's all the way to c, and then you subtract this distance here, which is the height of the function. That's why it's c minus g of y, that's big R. And little r is c minus f of y. And then those go into the formula. Then if c is to the left of the y-axis, it would actually be a negative number. So we've got f of y minus c, but in effect, it's going to be f of y minus negative c. So that would be f of y plus c, because we've got the height of the function here, and then we're adding that gap to it. So big R, f of y minus c, and then little r, g of y minus c. And there we go. There's our formula. Find the volume approximation of the solid generated by rotating the region bounded by y equals the cube root of x, the x-axis, and the line x equals 1 about the line x equals 2. So that's what that's going to look like. And because we're rotating around a line that's parallel to the y-axis, x equals 2, that's our axis of rotation, we're going to be doing a dy equation. So we're going to have to solve for x in terms of y. So y equals the cube root of x is going to be x equals y cubed. So the outer radius is 2 minus y cubed, and the inner radius, 2 minus 1, because that's where they said we were stopping, right here. Now, what would the bounds of integration be? Because we are doing a dy situation here, then I need y bounds. So that's going to go from 0 to 1. And so there we go. Here we've got our big R squared, little r squared. Pop that into the calculator. You get 6.7319 units cubed. Okay, now this one's a little bit tricky because we've got y equals x squared and y equals 4. That's what we're doing. So we're going around the line x equals 3. So there's the line x equals 3. And so it's going to be a dy situation here. So we know the bounds are going to be from 0 to 4, like that. Now, if I solve for x, I take y equals x squared and I solve for x, I get plus or minus root y. And this part here on the left side, that is the negative root y section. And on the right side, that's the positive root y section. So my big R is going to be 3 minus the negative root y section because I got to get all the way to that side. So it's actually 3 plus root y. And then little r is going to be 3 minus the positive part, 3 minus root y. So there, I can put it into my integral expression. I've got pi, and then I'm going from 0 to 4. We talked about that. Big R squared minus little r squared. dy, that goes into your calculator, about 201 units cubed. All right, so find the volume approximation generated by the regions 2 root x and y equals x about the line x equals negative 2. Okie dokie, so we have a negative axis of rotation. It's parallel to the y-axis, so we're going to be in a dy situation here. And because of that, this y equals 2 root x, I'm going to have to solve that in terms of x. X equals 1/2 y squared. Okay, so now what is my big R? It's going to the farthest part from the axis of rotation, so that's going to be y minus negative 2. So that's the function minus the axis of rotation, which happens to be negative. So that's going to end up being y plus 2. And then to the closer part, here's where we solve for x. 1/2 y squared minus negative 2 would give us 1/4 y squared plus 2. What are the bounds of the function? Well, the bounds of the function are going to be wherever these two guys meet up. And you can see by the graph here, these are going to be y bounds. So we're going from 0 to 4. And there's the function. And yeah, plug it into the calculator and you get 60 units cubed. Here we have y equals the cube root of x, y equals 0, and x equals 8 about the line x equals 8. Interesting. So notice that my region is butting up against my axis of rotation, and that's important because there's not going to be a hole in this one. So again, we're about the line x equals 8. So we know we have a dy. So the cube root of x is going to become x equals y cubed. And big R is going to be 8 minus y cubed. All right, that goes to the far side of the function. Now the close side of the function, normally we'd have a hole there. There's not a hole there, which means our inner radius is nothing. So we're just going to have a big R, and then the bounds are going to be wherever y equals the cube root of x matches up with the line x equals 8. So that's going to be from 0 to 2. So it's just a big R squared. It's a disk instead of a washer this time. 258.5 units cubed. Okay, we've got 2 root x, y equals 6, the y-axis, and the line y equals 6. Here's the line y equals 6. That's parallel to the x-axis. So we're going to have a dx. And let's see, y equals 2 root x. Okay, that's the farthest function. So my axis of rotation minus the function is going to be the big R. And then my inner radius, again, the function goes right up to the axis of rotation. So I just don't have an inner radius. So it's just going to be a big R squared right there. And then my bounds, okay, my bounds are where 2 root x matches up with y equals 6. So I can solve for that, and I get the bounds of 0 to 9. And there we have it, 169.646 units cubed. And we're done. Floating functions around other axes, you guys can do it all now. Thanks for being here.